Besides all of the interactions in the detector itself, the materials around the detector contribute to the final output. Let's stare at this picture for a minute, and if you understand all of the parts, you are a long way down the road. If we choose this gamma coming from the source, we see that it interacts by pair production in the detector, creating a positron and an electron. The positron, after depositing its kinetic energy, interacts with an electron and creates two annihilation photons, each having 511 keV. One or both of the photons can escape the detector, or both could interact within the detector itself to create a full energy peak. Iodine characteristic X-rays can escape from the detector, and the detector response will be lowered by the energy of the iodine characteristic X-ray, 28 keV. Looking at this gamma ray from the source, we see that it has a photoelectric interaction, creating an energetic photoelectron. This electron ionizes the scintillation material that releases UV photons during de-excitation. Some of these UV photons bounce around in the detector, guided by reflectors surrounding the scintillator, and some head in the right direction at birth. But overall, fewer than a third will strike the photocathode. About 10% of those photons striking the photocathode will free an electron and start the cascade down the dynode string. Now, let's focus on the surrounding materials. This gamma from the source strikes lead shielding surrounding the detector, creating a positron that annihilates, creating a 511 keV photon that can now enter the detector. Well, so what? Well, we're trying to measure the radiation coming from the source, and this 511 photon is not from the source. As shown here, a gamma from the source can suffer a Compton interaction in the shielding, and the resulting Compton photon can be counted. And as before, this is not part of the original spectrum. With any gamma interacting in the shielding, lead characteristic X-rays will be produced. These can also enter the detector, and again, they're not part of the source spectrum. And finally, there are backscatter effects. If scattering material is present behind the detector, the returning gamma rays create a pseudo-peak. Why does this happen? Because of the physics of Compton scatter, gamma rays from 5 MeV to a few hundred keV all return with energies between about 170 to 220 keV for scattering angles between 120 and 180. As you can see here, this is important for uranium-235 counting because the principal identification energy is 186 keV. I'll show you an example of backscatter peak in a minute.